Hello, good day to everyone. I am Johanna Calbe and I am part of Group 5 here to introduce to you our topic for the second module, which is industrial gases. Together with Marc David and Matthew Suarez, we will discuss throughout this whole video report the brief background and history of industrial gases together with its manufacturing process of some of the most major products in the industry. So to start, what are industrial gases? Industrial gases are a group of gases that are specifically manufactured for use in various industries, including petrochemical, medical, food, electronics, and steel industries, to name a few. The main gases produced are nitrogen, oxygen, carbon dioxide, argon, hydrogen, helium, and acetylene. So, for its brief history, the production and use of industrial gases dates back to the late 19th and early 20th centuries. In 1885, Carl von Lindt started the first industrial production of liquid air, paving the way for mass production of industrial gases. His methods for gas liquefaction and separation, mainly the Lindt process, are still widely used until today. Throughout the 20th century, advancements in chemical engineering and technology led to the development of more efficient and diverse methods for producing industrial gases. To add, in the mid-20th century, industrial gases began to be used in novel ways, such as in the development of the steel industry, where oxygen was used to enhance the efficiency of steel production. The industrial gas industry continues to be an important global market today, with uses in nearly every sector of the economy, from creating the right atmosphere for food preservation to aiding in healthcare and manufacturing processes. The significance of these gases cannot be understated. So, one of the most common products in the industry is oxygen. What is oxygen? Oxygen is a colorless, odorless gas that makes up about 21% of the Earth's atmosphere. It's essential for life as we know it because it's used in the respiration processes of many organisms. In the industrial gases industry, oxygen is produced on a large scale using methods such as cryogenic distillation and pressure ring adsorption, as I mentioned earlier. Now, onto its industrial uses. Oxygen can be used in the steel industry. In the steel industry, oxygen is used in large quantities in blast furnaces to convert irons into steel by oxidizing the impurities in iron. It helps increase the efficiency of the furnace, reduce emissions, and improve the quality of the steel. And in the healthcare industry, oxygen is used in hospitals. Oxygen is used in therapies for patients with respiratory issues or who need supplemental oxygen. This can include people with chronic obstructive pulmonary diseases or COPD, pneumonia, or those undergoing surgery. Lastly, it can also be used in water treatment. Oxygen can be used to enhance the effectiveness of wastewater treatment processes. By increasing the oxygen concentration in water, harmful bacteria and other microorganisms can be more effectively broken down. So in short, oxygen is a vital product produced and supplied by this industry. Its production and use across various sectors underline its importance in our modern economy. So, for the first manufacturing process, I'm here to introduce the pressure swing adsorption for nitrogen. So what is pressure swing adsorption? Pressure swing adsorption is a technology used to separate some specific gases from a mixture of gases under pressure according to the species, molecular characteristics, and affinity for an adsorbent material. It operates at near ambient temperatures and differs significantly from cryogenic distillation techniques of gas separation. In simple terms, PSA technique involves trapping targeted gases at high pressure and then releasing these gases when the system pressure is reduced. So for the first manufacturing process, I will discuss pressure swing adsorption, PSA, in a nitrogen gas plant. So this PSA technique, for the primary material used in a nitrogen gas plant is air. This is because air which we breathe is primarily composed of nitrogen, which is 78%, and oxygen, which is 21%, with the remainder being trace gases like argon and carbon dioxide. So, as we can see here, this is the flow scheme of the PSA nitrogen gas plant. So the air first go to an air compressor. This is where ambient air is drawn in and compressed. Compressing the air allows for a higher volume to be processed, and it also increases the efficiency of the adsorption in the PSA units. Next, after going through the air compressor, it goes to an aftercooler. So after compression, the air temperature is generally high due to the heat of compression. The aftercooler cools down this air, which not only makes it safer to work with but also improves the efficiency of downstream processes. Next, it goes through the PSA units. Here is where the pressure swing adsorption occurs. As described before, the compressed and cooled air is passed through a vessel containing a carbon molecular sieve. This vessel preferentially absorbs oxygen and other trace gases under high pressure, allowing nitrogen to pass through. This is why this flow scheme is the MS model, because it has the molecular sieve. So after going through the PSA units, it goes through an N2 of the nitrogen surge vessel. The nitrogen gas from the PSA units goes to a surge vessel, which acts as a buffer and storage vessel to accommodate fluctuations in demand or supply of nitrogen gas. And then, after going through the surge vessel, it goes to a Diox reactor. If the nitrogen gas needs to be of very high purity, a deoxyreactor might be used. In a deoxyreactor, a small quantity of hydrogen is mixed with the nitrogen gas and passed over a catalyst at high temperature. Any remaining traces of oxygen react with the hydrogen to form water, which can be easily removed. And finally, it goes through an N2 to a nitrogen dryer before exiting the process. So finally, the nitrogen gas is passed through a dryer to remove the water formed in the deoxyreactor and any other residual moisture. This ensures that the produced nitrogen gas is dry and suitable for its intended application. So after going through this entire process, the result in the production will be of high purity dry nitrogen gas from ambient air. So for this process, the byproducts of this are primarily the gases not collected as the main product, which include oxygen and trace gases. These are often vented out to the atmosphere during the regeneration cycle of the PSA processes. So, the main product of this is a high purity nitrogen gas, as I've said earlier. Depending on the setup and requirements of the PSA system, nitrogen of up to 99.99% purity can be achieved. This nitrogen gas is used across several industries, including chemical, pharmaceutical, food packaging, electronics, and steel industries, among others.
Our second major product on the gas industry is the manufacturing process of oxygen. Most commercial oxygen is produced using a variation of the cryogenic distillation process originally developed in 1895. This process produces oxygen that is 99% pure. More recently, the more energy-efficient vacuum swing adsorption process has been used for a limited number of applications that do not require oxygen with more than 90 to 93% purity. Here is the example of oxygen process flow diagram. First, the air is compressed to about 94 psi in a multi-stage compressor. It then passes through a water cooled after cooler to condense any water vapor, and the condensed water is removed in a water separator. The air passes through a molecular sieve adsorber. The adsorber contains zeolite and silica gel-type adsorbents, which trap the carbon dioxide, heavier hydrocarbons, and any remaining traces of water vapor. Periodically, the adsorber is flushed clean to remove the trapped impurities. This usually requires two adsorbers operating in parallel so that one can continue to process the airflow while the other one is flushed. The pre-treated airstream is split into two. First, a small portion of the air is diverted through a compressor, where its pressure is boosted. So here is the compressor. It is then cooled and allowed to expand to nearly atmospheric pressure. And this, the circle blue is the cooler. This expansion rapidly cools the air, which is injected into the cryogenic section to provide the required cold temperatures for operation. The second is the main stream of air passes through one side of a pair of plate fin heat exchangers operating in series. So this is the main stream of air that will pass through the main heat exchangers. The incoming air is cooled while the oxygen and nitrogen are warm. In some operations, the air may be cooled by passing it through an expansion valve instead of the second heat exchanger. In either case, the temperature of the air is lowered to the point where the oxygen, which has the highest boiling point, starts to liquefy. The airstream, now part liquid and part gas, enters the base of the high-pressure fractioning column. As they work its way up to the column, it loses additional heat. The oxygen continues to liquefy, forming an oxygen-rich mixture in the bottom of the column, while most of the nitrogen and argon flow to the top as a vapor. The liquid oxygen mixture, called crude liquid oxygen, is drawn out of the bottom of the lower fractioning column and is cooled further in the subcooler. Part of this stream is allowed to expand to nearly atmospheric and is fed to the low pressure fractioning column. As the crude liquid oxygen works its way down the column, most of the remaining nitrogen and argon separate, leaving 99.5% pure oxygen at the bottom of the column. Meanwhile, the nitrogen or argon vapor from the top of the high-pressure column is cooled further in the subcooler. The mixed vapor is allowed to expand to nearly atmospheric pressure and is fed into the top of the pressure low-pressure fractioning column. As of the argon vapor reaches a point about two-thirds the way down the column, the argon concentration reaches its maximum of about 7 to 12% and is drawn off into a third fractioning column, where it is further recirculated and refined. The final product is a stream of crude argon containing 93 to 96% argon, 2 to 5% oxygen, and the balanced nitrogen with traces of other gases. Things to remember: if higher purity is needed, one or more additional fractioning column may be added in conjunction with the low-pressure column to further refine the oxygen product. In some cases, the oxygen may also be passed over a catalyst to oxidize any hydrocarbons. This process produces carbon dioxide and water vapor, which are then captured and removed. Before processing, air is pre-treated to remove impurities that will clog the cryogenic piping. Once pre-treated, the air is submitted to fractional distillation. In the fractional distillation process, the components are gradually separated in several stages because all distillation processes work on the principle of boiling a liquid to separate one or more of the components. A cryogenic section is required to provide the very low temperatures needed to liquefy the gas components. Once the liquid oxygen is separated, it is purified and stored.
For the third manufacturing process of industrial gases, we have carbon dioxide. They offer a range of carbon dioxide production plants that are designed to be compact, user-friendly, and fully automated. These plants can be operated using different fuel sources such as diesel, natural gas, or kerosene. The carbon dioxide plants utilize a controlled fuel combustion process to produce flue gas with a high concentration of carbon dioxide. It has various types of carbon dioxide production plants available to cater to different requirements. These include diesel-fired, natural gas-based, biomass-based, and charcoal-fired based carbon dioxide production plants. So this is the flow diagram process of carbon dioxide plant. There are various methods are being developed to separate carbon dioxide from flue gases, with absorption processes utilizing aqueous solutions of chemical absorbents being the most prominent technology. The typical flow sheet for carbon dioxide recovery using chemical absorbents involves several distinct steps. First one is flue gas cooling and absorption. The flue gas is first cooled and then brought into contact with the chemical absorbent in an absorber. A blower is used to pump the gas through the absorber. At temperature ranging from 40 to 60 degrees Celsius, the carbon dioxide in the gas is bound by the chemical absorbent. Second is water wash section. After passing through the absorber, the flue gas goes through a water wash section. This step serves to balance the water content in the system and remove any droplets or vapor that may have carried over from the absorber. The clean flue gas exits the absorber. Next is stripper operation. The rich absorbent solution, which now contains the chemically bound carbon dioxide, is pumped to the top of a stripper using a heat exchanger. The regeneration of the chemical absorbent takes place in the stripper at elevated temperature that are typically between 100 to 140 degrees Celsius and pressures ranging from 1 to 2 bar. Heat is supplied to the reboiler to maintain the necessary regeneration conditions. This thermal energy input is required to heat up the solution and provide the desorption heat needed to remove the chemically bound carbon dioxide. Steam is used as a stripping gas and is recovered in the condenser, then fed back to the stripper. The resulting carbon dioxide product gas is separated from the condenser. The fourth step is carbon dioxide product and composition. The carbon dioxide product obtained from this process is relatively pure, with a purity level exceeding 99%. The main additional component in the product is water vapor. Due to the selective nature of the chemical absorption process, the concentration of inert gases in the production is low. And lastly is lean absorbent recycling. The lean absorbent solution, which now contains a significantly reduced amount of carbon dioxide, is pumped back to the absorber. This is achieved through the lean-rich heat exchanger and the cooler that lowers its temperature to match the absorber's operating level. This recycling of the absorbent ensures its continuous use in the absorption process. In conclusion, the described process achieves carbon dioxide removal levels typically around 90%, providing a relatively pure carbon dioxide product suitable for various applications. These are these are the sources that we use in our report. That's all of our report, and thank you for listening.